In this lecture we're going to extend our analysis of annuities. In reality, we often have to deal with something called an annuity due. Consider our example of kids going to college. And here you have, in 8 years' time, your child is going to be attending the college, and you estimate that to cover the cost of college you're going to need $95,000 in 8 years' time. Rather than invest a lump sum, you decide to make a monthly payment into your savings account. How much you have to pay in each month in order to have $95,000 in 8 years' time. In previous lectures we assumed that the first payment would be in 1 month's time. But suppose the first payment is today. You're still going to make 96 payments. How much will you have to pay each month? This is what we would call an annuity due. The first payment is today, whereas with a normal annuity, the first payment is in 1 month's time. To understand the differences between an annuity and annuity due, let's consider some timelines. With the annuity that we've seen in previous lectures, we know that the payments start 1 period from today. And we know that after 96 payments, the future value, or the value of all those payments invested over the 96 months, should come to $95,000. With an annuity due, the first payment is not 1 month from today, it is today. And we still make 96 payments in total, but the last payment is in month 95. And all these payments will grow to a future value equal to $95,000 after 96 months. What you can see is that we have shifted all the payments back 1 month relative to an annuity. This means that for each payment that we used to make under an annuity, with an annuity due, we get an extra period of interest. Look at the investment in month 1. Here's our first payment under the annuity. It comes in 1 month's time, whereas with the annuity due, the payment is made today, and so it will earn interest over the first month, which we wouldn't have earned using the annuity. The same is true for the second payment. We also earn an additional month of interest under the annuity due. Indeed, it's also true when we look at the final payment as well. We earn an additional month of interest with the annuity due. So what do you think will be the impact on the payment we have to make each month in order to have $95,000 in 96 months' time? Will the payment be lower for the annuity or the annuity due? Well, because we get an extra period of interest on each payment that we make with the annuity due, we would expect that we would have to pay less each month in order to have a future value of $95,000 in 96 months' time, because we earn that extra interest on every single payment that we make. So that should reduce our monthly payment. In terms of formulas, we know from previous lectures that the formula for an annuity is that the present value at time small t is equal to the payment that starts at time t plus 1 divided by the discount rate, or multiplied by 1 minus 1 over 1 plus r to the power capital T. Now with an annuity due, we know that the payments start today, and because of that we earn an extra month of interest relative to the annuity. So what we're going to do is modify the annuity formula, and the present value at time small t is equal to the payment, which now starts at time small t as well, so it starts today, divided by the discount rate, all multiplied by 1 minus 1 over 1 plus r to the power t. But we know that this must be multiplied by 1 plus r. Why? Because we know that for every payment we make, we earn an extra period of interest. So by multiplying by 1 plus r, we get that extra period of interest. That's the only modification we have to make to the formula for an annuity. We now have the formula to calculate the present value of an annuity due. Let's see how this formula works in reality. First, we need to calculate the present value of the $95,000. We know that in 8 years we want $95,000, but our annuity formula and our annuity due formula doesn't have future value, it has present value. First we're going to bring the future value back to the present using our present value formula. We know all the inputs, so we know that the present value is equal to the future value divided by 1 plus r to the power t, which equals 95,000 divided by 1.004583 to the power 96, which equals $61,246.95. Now that we know the present value of the $95,000 in 96 months' time, we can use our annuity due formula. Present value times small t is equal to the payment at time small t divided by the discount rate, all multiplied by 1 minus 1 over 1 plus r to the power t, all multiplied by 1 plus r. If we plug in the numbers, we can solve for the periodic payment C. We've got 61,246.95, and that's equal to C divided by 0.004583, all multiplied by 1 minus 1 over 1.004583 to the power 96, and that is going to be multiplied by 1.004583. If we do that calculation, I get C divided by 0.004583 multiplied by 0.3552953 times by 1.004583, which leads to 77.879908 C. Now we divide both sides by 77.8799, and we're left with C is equal to 61,246.95 divided by 77.879908, which equals 786.43. That is our monthly payment. Now, what was the monthly payment for the annuity? Well, under the annuity, the monthly payment was 790.03. With the annuity due, the monthly payment is 786.43. So our intuition was correct, that the payments each month would be smaller if we started making the payments today, because we get that extra period of interest. on every single payment that we make. So there's the difference between an annuity and an annuity due. We can also reverse this problem. Suppose a trust fund has been set up for your child and your parents contribute $786.43 per month, with the first payment starting today. They're going to make 96 monthly payments in total, and we know what the interest rate is per month. It's 0.4583%. How much will this fund be worth in 8 years' time? We've seen a similar problem before, and we know the first thing we have to do is calculate the present value of this stream of cash flows that our parents are making. Can we use the annuity formula to calculate the future value? Well, first of all, we know that annuity formulas calculate the present value, not the future value. But we know we can convert the present value into the future value very simply. The other problem we have is that we know the payments start today, not 1 month into the future. That means we can't use the annuity formula. We need the annuity due formula. And we can plug in some numbers to the annuity due formula. So we know the present value is going to be equal to the monthly payment, which we know is 786.43, divided by the discount rate, which is 0.004583, all multiplied by 1 minus 1 over 1.004583 to the power 96. And all of that is going to be multiplied by 1.004583. That's our formula for the annuity due. If we do this calculation, we get the present value. So we get that the present value is equal to 61,247.09. Now we have the present value, we can get the future value. To get the future value, we're going to use the formula FV equals the present value times by 1 plus R all to the power capital T, which is going to be equal to 61,247.09 times by 1.004583 to the power 96. And when I do that calculation, I get 95,030 cents. Why don't we get 95,000 exactly? Why do we get 95,030 cents? That's due to rounding errors. If I use the monthly payment calculator to 5 or 6 decimal places, rather than just to 2 decimal places, I'd be getting much closer to 95,000 exact. So the difference is a rounding error. We've now seen examples involving the annuity formula and the annuity due formula. We're going to see more examples in class and in homework problems, but that's all I want to cover today. See you in class.